Welcome to Biogas Basics. My name is Jürgen Kuber, and this short presentation discusses how to set up gas consumers and gas storage. I want to address the common assumption that biogas plants must be operated with full gas domes to have enough biogas available in case of breakdown of the feeding system. I will make the case to operate the gas domes as empty as possible to prevent flaring instead. As an example, I use a biomethane injection plant where the majority of the biogas is consumed by the biogas upgrader and a small percentage of the biogas is fed to a CHP to cover the parasitic power demand of the plant. The gas consumer throughput depends on the gas dome level. The functional relationship is defined with 2 points. Each has an X and a Y coordinate, which can be set in the SCADA. In this figure, the gas consumer operates at 50% load at gas dome levels below 30%. Between 30% and 80% gas dome level, the gas consumer ramps up from 50% to 100% output. Above 80% gas dome level, the gas consumer operates at 100% throughput. In this example, the gas consumer operates at 80% capacity when the gas dome has a level of 60%. However, this relationship also works in reverse. When the gas consumer operates at 80% capacity, it consumes a certain amount of biogas. In a steady state, or over a long period, the plant produces as much biogas as the gas consumers consume. The y-axis shows the equivalent biogas production of the plant. The gas dome will assume a level that corresponds to the projection of the gas production of the plant onto the x-axis. In our example, the gas dome will on average be at 60% level, if the plant makes on average enough gas to run the gas consumer at 80% capacity. If the gas production increases, the gas dome will begin to fill up. The higher gas dome level will lead to a higher gas consumption and a new steady state will form. In this example, if the biogas production increases so that it corresponds to the gas demand of the gas consumer operating at 85% capacity, the level in the gas dome will increase to 65%. This system creates a feedback loop. During normal operation, we will try to operate near 100% output. The gas dome assumes a high level, here almost 80%. Now this is the important bit. We should select the points on this curve, so that the gas dome level is at around 50% when the gas consumers operate at 100%. Let's take a moment to consider the purpose of gas storage. If the gas consumers have a problem, for example the CHP or upgrader trips, the grid operator shuts down injection, or there is a PLC problem, the gas storage can store gas for a while before the flare must be activated. In case the feeding stops, because of a feed hopper or pump breakdown, we want to ensure that there is enough gas to keep the gas consumers running. Only that the latter is not true, at least if the gas consumers do not operate at full capacity during normal operation. There is no advantage in storing gas in the gas dome before it is upgraded. As long as it hasn't been injected to the grid, something can still go wrong that will lead to flaring and loss of the produced biogas. In case we have too much gas, we can always ramp up the upgrader and inject that gas. Once the gas is in the grid, it is sold, and the risk is no longer that of the biogas plant. There's a second reason why we should operate the gas dome as empty as possible. If the gas production is above the gas consumption, the feedback control loop is broken. The upgrader cannot ramp up to over 100% capacity. Instead, more biogas will be produced than consumed and the gas dome level will rise continuously. Keeping the plant at 100% output requires operator intervention. We will need to adjust the feed rate to match the gas production exactly to the consumption of the gas consumer at full output. We need to change the feed and observe if the gas dome level increases further or starts to decrease. This is much easier when 50% of the gas dome is available than in the previous example, where only 20% of the gas dome could be used to synchronize feeding with the gas consumption at full output. Ideally, the adjustment of feeding is automated using a feedback controller. I will do a presentation about feed control in the future. The CHP control must be adapted to the upgrader control. This figure shows the relative percentage of biogas uptake by the CHP in orange, upgrader in blue, and flare in green as a function of the gas dome level. The CHP takes around 10% and the upgrader 90% of the total nominal biogas production. The flare can burn more than the nominal biogas production. CHPs with a digestate dryer or on a high export tariff should run flat out and only throttle down when the gas dome is almost empty. The biogas upgrader is the main gas consumer and should operate at full capacity when the gas dome is half full. The flare kicks in when the gas dome is almost completely full. It stops when the level has dropped by a couple %. For completeness' sake, it should be mentioned that a few biogas plants use different methods to control the biogas flow to the gas consumers. I have seen control philosophies for the gas consumer system that use a PI controller to regulate the biogas flow to the gas consumer. Biogas flows into the gas dome, which serves as the control system and acts as a storage vessel. The objective is to maintain the gas level inside the dome at a specified set point. The actual gas level is the control variable. It is continuously measured and compared to the set point to calculate the control error, defined as the difference between the set point and the measured gas level. This error signal is processed by the PI controller, which calculates the control output. It serves as the set point for the gas consumer, which is the final control element in the system. By adjusting the biogas flow, the gas consumer influences the level in the dome, closing the feedback loop. In this arrangement, the gas dome will always be near its set point, and the biogas consumer will take up the average gas production. It is not possible to set the gas consumer to maximal capacity. If the biogas production meets or exceeds the maximum consumption capacity of the gas consumer, the system operates without feedback control, causing the controller to wind up. Generally, this control philosophy is not recommended. To conclude, we want to minimize flaring and use the biogas dome to store biogas when there is a problem with the biogas upgrader or grid entry unit. The upgrader control should be set so that the upgrader operates at full capacity when the gas dome is half full. There is no need to store biogas on site prior to injection. Biogas that hasn't been injected can still be flared. Once it has been injected, the risk has been transferred to the grid operator. Manually adjust the feeding to keep the gas dome level between 50% and 100%, or use a feedback control loop to adjust feeding so that the gas dome level stays constant at a value where the biogas upgrader operates at target output. This maximizes the plant output and minimizes flaring. If the plant is already at its feeding maximum and the upgrader is not at its maximal flow rate, the gas storage level will stabilize under the 50% level and no intervention is required. Simply maximize feeding. If the site has a CHP to cover the parasitic power demand of the biogas upgrader, it will need only around 10% of the total biogas production. Make sure that a low gas dome level does not restrict the CHP. Set the CHP control parameters so that the CHP operates at full capacity as soon as there is some gas in the gas dome. This concludes the presentation about setting up the gas consumer controls. I hope you learned something new, and I see you in the next episode of Biogas Basics.